시작하겠습니다. 안녕하세요. 반갑습니다. 퀀텀 웨비나에 참석해 주셔서 진심으로 감사드립니다. 저는 메가존클라우드 퀀텀 이노베이션 랩의 유닛 리더 김희현영입니다. 저희를 잠시 소개드리자면 저희는 아마존 브레킷, 마이크로소프트 애저 퀀텀 등 다양한 양자 클라우드 서비스를 제공하고 있고 양자 기술의 산업 적용을 목표로 교육, 컨설팅, 그리고 글로벌 파트너십을 추진하고 있습니다. 저희는 키스티와 함께 추진 중인 양자 컴퓨팅 서비스 및 활용 체계 구축 사업의 일환으로 본 웨비나 세션을 마련했고, 오늘은 네덜란드 델프트에 기반을 둔 양자 컴퓨팅 기업 퀀트웨어의 파티세걸스를 모셨습니다. 퀀트웨어는 초전도체 기반의 양자 프로세서를 설계하고 제조하는 회사로 대규모 양자 컴퓨터 구현을 목표로 기술을 개발하고 있습니다. 강의 중 질문이 있으신 분들께서는 줌 화면 하단에 Q&A 창을 통해 질문 남겨주시면 Q&A 세션을 통해 여사분께 전달드릴 예정입니다. Hello everyone, thank you for joining us today for the second session of our April Quantum Webinar Series. I'm Hyunyoung Kim from 메가존클라우드 Quantum Innovation Lab. We organized this webinar to highlight key technology trends in quantum computing. And today we are happy to welcome Bart Segers, Interim Head of Marketing at QuantWare. QuantWare builds superconducting quantum processors with a strong focus on scalable system design. Bart will talk about the key challenges in scaling quantum hardware and how QuantWare is working to solve them on the path to utility-scale quantum computing. Now I'll hand it over to Bart. Hi, Bart.
Hi, thank you for having me on this webinar. Really great to speak here.
Mhm.
Like you introduced, I'm from QuantWare. At QuantWare, we make superconducting quantum processors. And Korea has always been an important region for us, actually, since the beginning. Since we started, Korea was always one of the most interesting regions for us. So really great to speak here and connect with the Korean ecosystem. So my name is Bart Segers. I'm head of marketing at QuantWare. I have a background in physics, so I studied physics at the TU Delft, graduated in QTech, which is one of the leading quantum institutes in the world, and the main quantum institute in the Netherlands. And also the place where QuantWare was sort of a spin out from 5 years ago. So maybe a brief summary of QuantWare. So QuantWare started in 2021 as a spin out from QTech and the TU Delft in Delft in the Netherlands, with a mission to solve QPU scalability worldwide. So to make a solution to scale quantum processors and make it available to the entire quantum ecosystem and industry to build more powerful quantum computers on. So we started that in 2021 when we launched back then the world's first commercially available QPU. So before that, you could only buy a full closed system, like a full stack system from, say, IBM but it was not possible to buy just the QPU and build your system with that. So you either had to buy a full closed system or you had to build everything from scratch. You had to build your own quantum fabrication facility in order to build a quantum computer. That's somewhat similar to how the normal classical computer industry started in the 50s and 60s. Back then, everyone started with building full stack system. And then at some point, Intel only specialized on the quantum processor, and that sort of became the standard business model in that industry. So that there are some similarities there. That we started in 2021, and that quite rapidly grew to a customer base all over the world. We have customers in 20 countries, and that sort of started a new business model for quantum companies to build their own quantum computers and really specialized on building systems, being a system integrator, but not necessarily building your QPU from scratch, but buying that from a specialized quantum processor company like QuantWare. that is what we've been most known for growing our customer base on these QPUs. In the meantime, what we've been mostly developing internally is a scalable architecture to scale QPUs. That is called VIO, and that's what we've been working on basically since the beginning. And we've now, since end of 2025, started to really openly talk about that more and more. And in December 2025, at Q2B Silicon Valley, we launched VIO 40K, which is a generation of VIO that can host the first 10,000 qubits quantum processors, which we're able to ship for the first time in 2028. So we're launching it now. So the first customers we can already engage with, so they're ready to build those 10,000 qubit systems in 2028. So that's a brief overview, and now I'll go in a bit more depth of what we do. So maybe to start, really at the beginning, what are we trying to do here? So the goal here is for QuantWare to power systems that can deliver like real economic value and real value to humanity. And for that, we need to scale quantum computers to much larger sizes. So that's sort of the first requirement you have to meet. You have to scale to hundreds of logical qubits in a system, because that, if you look at all of the different applications, a lot of them you can really start doing from the hundreds of logical qubits. So that's the key first thing you need to meet with your quantum system. You need to grow it to have sufficient capacity in terms of logical qubits. And that's, I think, the topic that people mostly speak about in our industry. But there are actually two more requirements for a system that are equally important to be really of economic use to society. First of all, that for running these large quantum computations, that can take quite a long time. So fast processing speed of your system is actually very important. And you need to be able to execute your quantum workloads in a economically relevant time. So if it might take on one type of quantum computer, it takes a day to solve something, and on the other one, it takes a year. That makes obviously a very big difference on whether it's of economic use. And the other one is to, we live in a power constrained world. That's also a big bottleneck in AI data center build out right now. So quantum computers need to be competitive on a compute per watt level. And then, of course, you can debate how do you define compute, and that's a very interesting topic. But on a high level, you do need to be competitive on that metric as well. So that's sort of how we see where we need to go. Then there are multiple ways to build quantum computers. So we at QuantWare, we built superconducting systems, so with superconducting quantum processors. But there are like various other ways, neutral atoms, trapped ions, a couple of others, and all of them have different strengths. And so superconducting is typically mostly well suited for computing, and others maybe for memory or for quantum internet or communications. This is a graph from DARPA's HARC initiative about heterogeneous systems, so with multiple modalities. And this is sort of also how we see it, that superconducting systems are most fit for computing, and others have other strengths, and you might, in the end, build a system with multiple of these modalities to leverage the strengths of each of them. But so superconducting is really for compute. And the main reason for that is a really fundamental one, and that's that superconducting systems have the highest speed of operation. And that's a very relevant metric, also coming back to where we started with. running workloads in an economically relevant time scale is what will determine if these systems will be of actual use to society or not. And also they need to be competitive on a compute per watt basis. So if you can generate a lot more compute by being a lot quicker, that's very relevant. To sort of illustrate that, here's a comparison graph to breaking one RSA encryption key on a neutral atom system versus a superconducting system, based on it's slightly outdated now, but what were the best estimates to run Shor's algorithm. So a lot of theory people do all sorts of algorithm and compilation work to see how you can map an application on an actual hardware platform and do a resource estimation of that. So based on the best known resource estimations, you see that a superconducting system takes just a lot less resources to run the same algorithm. This is, like I said, slightly outdated now because there were a lot of algorithm developments in the past weeks. But still, the point is still the speed advantage is really what makes superconducting fit for compute. However, there's also a main thing that superconducting systems have struggled with over the past years, and that's to scale QPU size. Actually, superconducting has been one of the main modalities since the beginning of quantum computing. And in recent years, you actually see other modalities really catching up or taking over in terms of the amount of qubits they achieve in their systems. And that is really a really big bottleneck for superconducting systems that they need to overcome. And that is exactly the problem that we at QuantWare are committed to solving. So we want to make a quantum processor architecture, VIO, that scales superconducting QPUs from being the smallest of the modalities to the largest one. And that is really important for the quantum industry, because having larger QPUs is really needed to make the whole system competitive on all of these three requirements. Because you might say the obvious alternative, if you cannot make larger QPUs, but you still want to scale your quantum computer and scale the number of qubits, you might say, okay, we can also network smaller QPUs together to form a larger quantum computer, which is obviously a great way to do it. However, if you do that with small QPUs, it's really much more beneficial to do it with as large QPU nodes as possible. So in any case, even if you can network, which might be very useful in the future, it's still much better to have as large QPUs as possible. First of all, you do just need more qubits, and doing that on a monolithic QPU has by far the highest QEC efficiency, so number of physical qubits per logical qubit. So you will achieve the highest number of logical qubits on a monolithic system relatively, because you compare to a network system where you have more lossy links between QPUs. A monolithic chip has much better connectivity within the chip, which is a much more efficient way to scale your number of qubits. Also, compiling circuits on a monolithic system is more efficient than on a distributed system. And having one single compact QPU has minimal overhead in terms of you need just one fridge to cool it down. You need less qubits, therefore less cooling power, less control power. So in terms of competitiveness on compute per watt or compute per dollar, it's also really important that even if we might be able to network QPUs together, that we also still create as large QPUs as possible. Um, so that is really what at QuantWare we're trying to do, to create as large QPUs as possible. And to do that, we have developed a clever way, a clever architecture to build these systems that solves the fundamental bottlenecks that hold back scaling currently for superconducting quantum processors. So let's start by looking at what are exactly the bottlenecks in current quantum computers. So if you look at the image on the right, that is a typical sort of, if you have seen an open fridge in a superconducting lab, this is typically what you see. So you see here on the right, you see the QPU, which is a 2D chip typically with a PCB with connectors. And then there are a lot of quite bulky wires and bulky components which are used to amplify the signals or filter the signals that come from the QPU and need to go to room temperature. But all of these are very bulky and not integrated into one sort of chip. So for each of them, you need a separate housing, separate connectors, separate wires, which makes, if you have a system of, say, 50 qubits, if you look at pictures online as well, a fridge like this is already completely full with wires and components. And actually, the 50 qubit QPU is only a small part of that. And then within that, only a small part of the QPU is used for the actual qubits. So if you want to scale this to, say, 10,000 qubits, you would need 100 of those bulky fridges full of wires to scale there, which is just simply not feasible. So we need to find a solution for that as well. And then the last one, or the sort of other problem this creates, is that all of these components, they need to be cooled down as well, which, it generates heat, and that is a big burden on your power consumption of your system. So these are sort of what we see as the past, and what are really the fundamental bottlenecks that we need to solve. And this is the sort of the key requirements we have in mind when designing this VIO QPU architecture, that it needs to tackle all of these in one architecture. So diving into how VIO works. So the first fundamental thing is that in VIO, we route signals vertically to the qubit chip. So if you look at the picture here, this is of a conventional qubit chip. So not a VIO chip, but a sort of traditional QPU chip. And how those are typically built is that we have a chip. In the middle, we have a number of qubits. And each qubit needs a number of signal lines to control the qubit and to read out the qubit. In a system, or in a traditional 2D chip, those signals all come from the side of the chip to the middle. And if you scale the number of qubits, you very quickly end up with a complete mess and a lot of different lines that need to pass very closely to each other or cross each other, causing crosstalk. Also, you just need a lot of space to route out the signals, because you're limited by how the total length of the peripheral of your chip, which, if you scale the number of qubits, that scales in 2D, but the peripheral of your chip only scales in 1D, so that just blows up very quickly. So what the first thing we do really different in VIO is that we route all signals directly from the top to the qubits. So we have a qubit plane at the bottom with our qubits on it, and we route all signals from the top and route out also to the top. This has a couple of benefits. So we can create a much denser qubit chip because we don't need all that space to route out. We also free up the edges of the chip because normally we needed all the edges of the chip to route out signal lines, but now we don't need that anymore. So this actually allows us, which you'll see in 2 slides, to scale these chips modularly together and tile them together. The way we route signals from the top is by creating this horizontal qubit plane and placing vertical chips on top of them. These are similar to our qubit chips, just silicon chips, which actually has a lot of benefits. So we can integrate not just signal lines, but also these other components like filters and amplifiers that are currently very bulky. We can integrate all of that circuitry directly in the vertical chips, which solves this key bottleneck of bulky components. Also, because all of this is just silicon based, it's all parts are, we can make everything superconducting, causing no heat dissipation. We can produce it at an industrial scale because it's just repeating a process of chip making and then assembling them together. And third, and maybe most importantly for really reaching that scale, is that we can scale VIO modularly. So what we mean by that is that we can create these smaller modules, which we can make sure that we can achieve very high manufacturing yield for. And then we just scale by tiling those together and attaching them to form a large qubit array. And then at the bottom, we connect all of these smaller qubit chips together over high fidelity qubit to qubit connections. And it actually has been demonstrated also in-house, but also in literature, that these inter-chip qubit connections are actually very much on the same level as on-chip to qubit gate connections, which means that actually from a user perspective, although it consists of multiple chips, it's effectively a monolithic qubit plane, which has a lot of benefits in terms of compute efficiency and QEC efficiency. And then another benefit of VIO is that it's actually superconducting qubit agnostic. So it's compatible with any superconducting qubit type. So in-house here we make transmon qubits, which is maybe the most widely used superconducting qubit, but also more exotic qubits which have all sorts of benefits like cat qubits or fluxonium qubits. They can all be made compatible with VIO. And the reason for that is that you're looking here at the cross section of a VIO QPU, is that we have the vertical chips that route the signals and that integrate the components. And then we have a redistribution layer, and below that we have the what we call QMCMs, qubit multi-chip modules, and that's where the qubits are. And we can, with this redistribution layer, configure all of the lines in whatever configuration we need for that type of qubit chips. So maybe you need more flux lines or more drive lines. We can all configure that in whatever is required for that type of qubit chip. And because we build it up like this, another great advantage is that we can actually pre-test and pre-screen those qubit multi-chip modules separate from the whole system. So we don't need to integrate all of it and then measure everything and then find out, oh, this chip is not working. We can pre-test those and then select every chip that is of the quality we want and then integrate them into a QPU. So maybe to summarize how VIO works. So the first key thing is we route all signals vertically from the top. We do that by placing vertical silicon chips on top of a horizontal qubit plane. And these vertical silicon chips allow us to integrate these upstack components and to produce everything at an industrial scale. Then once we can create these modules, we can attach them together, and they form effectively a monolithic qubit chip with these high fidelity qubit chip-to-chip connections, which you see here at the bottom, a display of these smaller qubit chips that are tiled together with these high fidelity qubit connections. And then all of this fits actually in a quite compact form factor. So a 10,000 qubit QPU, so that's what you achieve with VIO 40K, our generation of VIO that we can ship in 2028. 10,000 qubits actually fits in 15 by 15 centimeters. And the reason for that is that everything is like limited by just only the footprint of the qubits themselves, because everything else we can fit directly above the qubit plane. So we have no fan out from the qubit plane, which is very different from how QPUs are built today with 2D chips that need a lot of space and bulky components. If you can fit everything directly on top of the qubits, you're just limited by how small you can make your qubits. And even with today's qubits sizes, which are not even maybe that small, you can fit 10,000 qubits in, say, about 15 by 15 centimeters, which has an enormous impact compared to systems today, because it means we can fit an actual large QPU that can create real impact in a single dilution refrigerator or cryostat, which is actually a cryostat that you can already that's already commercially available today. So the vendors can make that today already. And that's obviously very important for driving that compute per watt and compute per dollar metric, that you can achieve a lot of compute power in a relatively compact system. So if we zoom out to that full system, if you look at this render of a VIO system in a sort of data center environment, we have a monolithic single compact QPU that fits in a single cryostat, with all of these components integrated to minimize heat load. We don't need any bulky housings and components or non-superconducting parts in the cold stages of our fridge. And we can interface the QPU directly to these high density flexible cables to route signals from the coldest stage of the fridge to the room temperature, and then in the end to the room temperature electronics where the signals come from. And all of this can fit in a sort of typical dilution refrigerator that is already available today, and can be operated with a number of control racks that you can actually, that are also of very high technology readiness and very similar to the control racks we have today. So this is quite a mature system stack with not really a lot of risks in terms of low TRL components. All of these things have been demonstrated already and are often already commercially available with multiple vendors, which makes the stack very mature and ready for sort of a data center environment. So maybe bridging now to where we are today and how we are going to 10,000 qubit systems in 2028. So how we develop VIO is actually we've started with validating and the most key parts and sort of highest risk parts of VIO that are most unique to the architecture. So that's making that vertical to horizontal connection, doing that with TSVs and superconducting indium bumps and then the key requirements are that all of this maintains very high RF performance, so being able to transmit signals with very high fidelity, have very low crosstalk between channels, and have a high range of a high critical current, to have a high range to operate your system in. So those were the sort of the most core and unique parts of the VIO architecture and sort of the highest risks. So if we could achieve them, we have de-risked our architecture by the most amount. So that's what we've started with, and we've achieved all of those things and made the device VIO48, where we've measured excellent performance on those parameters. We're scaling from VIO to VIO 1K, and then by scaling up our production facility. So I'll get to that later as well, but we're building KiloFab in Delft, which is the production facility where we can really scale up our industrial production. And by just making more of these chips at higher fidelities, more reliable, we can scale from VIO48 to VIO 1K. Then simultaneously, we have demonstrated very high fidelity chiplet to chiplet connections. So we've achieved 99.4% fidelity between qubits of different chips, which is very similar to state-of-the-art on-chip qubit connections. And then the next step is to also be able to connect multiple modules together. And then if you can achieve both and you can make VIO 1K, you can scale modularly to VIO 40K. And then the other parallel track is component integration. So to scale to really 10,000 qubit systems, we also need to get rid of all of these bulky components. So we need to be able to integrate all of those into a single vertical chip by that time. So we're developing first the individual subcomponents, so two-pass amplifiers, filters, and isolators. Then the next step is to integrate all of those in a single readout module. So readout module contains all of the components that you need to read out your qubits with high fidelity, and then integrate those into VIO. And once we achieve all of that, we can just combine all of these different subparts and scale to VIO 40K. So that's how we go from sort of where we are today to VIO 40K in 2028. And then, as I already mentioned earlier, sort of one of the most key, I think, next steps for us to be able to execute on our roadmap is that we're building KiloFab, which will be the largest dedicated quantum open architecture QPU fab. So we really make QPUs on an open architecture available to the entire ecosystem to build systems on. That's really what we specialize on. And now we have one of the largest production facilities to produce this, which is a very important step for us to go from here to VIO 1K and then to VIO 40K. This facility will be placed in Delft, and it will consist of, first of all, clean room, where we produce the wafers just from scratch to the full wafer, where we also do the assembly and dicing of the wafers, and then the assembly into the VIO modules and attaching those together. And the last step is basically a test facility with cryogenic setups, where we can measure all of these chips and all of these QPUs, and then after that be able to ship them to customers. So that will be, we're building that now, and it will be live towards the end of 2026, so end of this year still. So that will be quite an important milestone for our company. So I come towards the end of the presentation now. I hope I've given a good impression to you of what VIO is, what sort of the fundamental bottlenecks in our industry are to get to these quantum computers that can solve real world problems in the real world that meet all of the requirements that they need to meet for that, and how our VIO QPU architecture is actually solving those and getting there on the shortest timeline as possible. Um, we're so thank you for listening. We're very keen to working with the Korean ecosystem. So if you're interested, I think we'll do some questions now, but we can also, of course, be in touch afterwards. I've put my email here on the slide as well, so feel free to reach out if you're interested in working with us later as well. So thank you very much.
Okay, at first, thank you for your presentation. So we got a couple of questions. So I'm going to translate the question into the Korea and then
Yep.
speak to the audience, and then we'll translate into the English.
Okay.
네, 오케이. So 먼저 첫 번째 질문은 그 2028년도에 이제 10K 큐빗, 그러니까 1만 큐비트를 목표로 한다고 했는데 이 중에서 실제로 구현 가능한 논리 큐비트 수는 어느 정도 예상하시나요? 라는 질문이 있었습니다. So the first question is about that when you say the 10K qubit in 2028, so how many logical qubits do you expect?
Yeah, so very good question. So that depends on a couple of things. So first of all, so the two main things are the qubits, the physical qubit fidelities that you can reach. So the difference between physical and logical qubits is that physical qubits are really the physical units, and then logical qubits is, how we encode a more protected qubit in multiple physical qubits. So how many physical qubits depends on on what quality your individual qubits have, and also what quantum error correction code you use. So one of the most widely used ones is the surface code, which is a 2D error correction code. But there are also more efficient quantum error correction codes that require less physical qubits per logical qubit while achieving the same distance or state of protectiveness. So there are a couple of factors, but say you encode a logical qubit with 100 of physical qubits, which is for a surface code sort of what the state of the art is now with the Willow chip of Google, for example, and with a more efficient code that's even better. But if you have 100 physical qubits per logical qubit, you would have 100 of logical qubits in a 10,000 qubit system.
Okay, thank you. And then the next question is, 2차원 그리드 구조 외에 다른 큐비트 레이아웃도 고려하고 계신가요? 큐비트 토폴로지에 따라 일부 알고리즘 구현에 제약이 있을 수 있기 때문입니다. 라는 질문입니다. So next question is that do you have a qubit layout other than the two-dimensional grid? Because the qubit topology, the implementation of some algorithm can be limited. About
Yeah, so
the grid question.
yeah, so we are actually compatible with also higher order connectivity than just 2D. So the sort of the minimal we achieve is always full 2D grid of nearest neighbor connections. So that's suitable for the surface code, for example. But the way VIO is built, maybe I can go back to that slide here. We already use multiple layers to route signals. So if you extend this, you can actually also create longer distance connections between qubits that are further away from each other than nearest neighbor. And in that way, you can build your system that has a higher order connectivity compatible with other QC codes. That being said, like full all-to-all connectivity, I think won't be feasible in a superconducting system because you would have to pay a lot of sort of hardware penalty to achieve that. where some others are more naturally suited for all-to-all connectivity. Um, um, but we can definitely make VIO compatible with these longer range connections.
Great, thank you. So I think the audience have a lot of questions, so I'm going to summarize it and ask you for the
Yep.
details. So
Yep.
next question, I'm going to ask for the next question. So, 스택 칩에 사용되는 소재는 어떤 것인가요? 소재 관련된 질문이 있었습니다. So the next question is about the materials. So what is the material of the stacked chips?
Sorry, the
The
metric?
material of the stack material.
Do you mean like what metric
Material.
we achieve with
Material, but not the metrics, the material.
I'm not sure I understand. So maybe to answer one question. So a couple of key metrics we have measured from the vertical chip stack is S to 1 transmission. So doing a full loop of your signal through the vertical chip stack and back. And we've achieved a transmission of less than or better than -2 dB transmission, which is actually very comparable to sort of the state of the art on planar chips today.
Sorry to
Also,
interrupt. I think
yeah.
that I may have miscommunicated. The question is about the material composition, about the
Oh,
chips.
material.
Yeah,
Material. Sorry.
material.
Yeah.
Yeah.
Yeah. So, the substrate is silicon based, and then we apply a number of metals and layers. I cannot disclose, unfortunately, like what exact materials we use for that. But it are a number of metals to make the circuitry that we need.
So I think when we think about the time, I can have a one or two questions will be enough for the finalize. So if you have another questions, the speaker mentioned the keep in touch will be better. So I'm going to give some last two questions. The first one is about um, uh, 그, okay, so uh, okay. 네. 그 큐비트를 모두 하나의 냉장 장치 안에 적층 구조로 수용하겠다는 계획에 대해서 좀 궁금한 점이 있습니다. 그 대규모 큐빅 시스템을 초전 상태인 밀리캡을 유지하기 위한 특별한 방법이 있나요? 라는 질문이 있었습니다. 질문이 좀 많다 보니까 지금 두 가지 질문을 하고 이제 나머지 궁금하신 것들은 이제 연사님한테 직접 좀 메일로 보내서 궁금증을 좀 해소하는 방안을 좀 안내드리도록 하겠습니다. So the question is about that you plan to house all the qubits in a single fridge using a stacked architecture. So is there any special method for maintaining such a large-scale qubit system and an ultra-low temperature of a millikelvin level?
Yeah, so actually, indeed, it is a very very good question. So basically, having enough cooling power and the thermalization of your system, that's actually a key thing we look at when designing our architecture. And we have done some simulation work on this, and we're also actively working with the different fridge vendors to see if we can together meet all the requirements to properly thermalize a 10,000 qubit system like that. And actually, that is very, very possible for a couple of sort of key reasons. And one of them is that VIO actually achieves very low heat dissipation because all parts in the millikelvin stage are superconducting. So we have no heat dissipation from that. And also, yeah, it's the cooling power availability is just there. So that's very valid question and something we do really look at. But indeed, it is possible to cool a system down with a system like that.
Okay. So, this will be the last question. 마지막 질문입니다. 칩랩 기반 구조에서 칩랩 칩랩 영자 영사는 동일 칩 내 연산보다 오류율이 더 높을 것으로 예상되는데, 현재 구현된 칩 간 연산의 피델리티 수준은 어느 정도인지 궁금합니다. So the last question is that chip-lab to chip-lab quantum operation must have a high error compared to intra-chip operation. So may I ask the fidelity of current chip-lab to chip-lab quantum operation?
Yeah, so we have achieved 99.4 chip-to-chip fidelity, which is not exactly the state of the art for on-chip connections. That's more like 99.9, but quite close to. And especially if you consider things like also the number of 2-qubit states on on-chip connections have been measured orders of magnitudes more times than chip-to-chip connections. And it actually seems more like the connection is not fundamentally limited by being chip to chip, but more just limited by coherence times. And so that makes us confident that actually we can achieve also the same fidelities intra-chip compared to on-chip.
Okay, so thank you for the answer. I think the audience will be satisfied about your kind response. Thank
Thank you
you.
so much. Yeah, thank you so much, and thank you for everyone who's listening, and thank you for having me on this webinar.
Okay, thank you, Hyunwoo and Bart. Many thanks for sharing your expertise. It was a fascinating session, and I'm sure it offered our audience a deeper understanding of scalable quantum hardware. And I think it's probably still morning for you, so hope
Yeah.
you enjoy the rest of your day.
It's a great start of the day. Yeah, thank you so much, and have a great rest of your day in Korea as well.